Picking up where we left off, we're going to talk now about cycloalkanes. So cyclic hydrocarbons, these are carbons that form a ring, and there's going to be two less hydrogens. So the ring formula is going to be CnH2n, the same as for what we're going to see later, an alkene. So when you do this, basically what you're doing is calculating the number of double bonds or rings. What's called the degree of unsaturation. All right, so when you look at the formula, you're going to notice that it's CnH2n and not CnH2n plus 2 because we had to form that ring, we got rid of two hydrogens. Now, cycloalkanes form tons of rings. In nature, these are multiple different sizes. In fact, 3 to 30 carbons have been found. 3 to 20 are more common, but 5 and 6 membered rings are probably the most common rings that we see. Now remember, the ring can be denoted as, it can be named as the parent chain, or it can be named as a substituent. But what we do when we name a ring is we put the word cyclo in front of it. So this has a ring of 4 carbons, cyclo, bute for 4, ane, meaning there's no double bonds. So even though we had that degree of unsaturation and we have CnH2n, it's still an alkane. There are no double bonds, so we are still naming it with an ane. Cyclo, it's a ring. Pent, it's a 5-membered ring. Ane means it's a 5-membered all single bond ring. So that's where we see a pentagon. Cyclohexane is a 6-membered. Cyclo means ring, hex means 6, and ane means all single bonds. So there we go. All right, so let's look at naming these. The prefix is always going to be cyclo for a cyclic hydrocarbon. If there's only one substituent on the ring, you don't actually need a number because no matter what, it will always be number 1. But if we have more than one substituent, you're going to start numbering the ring with the one that comes first alphabetically. So we would have to say this is methyl, and this is tert butyl. Which one comes first, B or M? Remember, we look at the B. If we do that, then if there's more than 2 substituents, you would number the ring so that you get the lowest numbers. So we'll look at that. So this one here, we have, what group is this? CH, CH3, CH3. If you remember from the last video, that is isopropyl because there's 3 carbons total. So this would be isopropyl cyclopentane. This one we would have to number. Which one gets number 1? The tert butyl or the methyl? Well, it's going to be the tert butyl because B comes before M. So 1, 2, 3, 4, 5, 6. It's going to be a cyclohexane, but it's going to be 1 tert butyl, 4 methyl cyclohexane. So that's a really long word, right? Really long name. A lot of these are. There are basic rings. I want you to pause it and try it. These are probably the most, basic ones we can give you. And then we'll start looking at some what are called geometric isomers. So pause it and try to give the names a whirl. This is cyclopropane, cyclohexane, and now we have chloro and methyl. Which one comes first? 1, 2, 3. So 1 chloro, 3 methyl cyclohexane. Sorry. All right, so this would be the name. I know it's a big, long name for this compound. Now that we have a ring, we have something else that comes into play. We have restricted rotation. So when we form the ring, we have restricted rotation. And we're going to talk about this on the upcoming slides. But first, I want to look at what it means really to have free rotation about a single bond. Because even though all the bonds in our alkanes, cyclic alkanes we're talking about, are still single bonds, they're not free to rotate anymore because they're locked into that ring formation. So starting with ethane, this is actually butane, but starting with ethane, we have what are called different conformations. Remember the conformers? This is basically as these carbons, I know you can't see my pointers, let me try this. As these carbons are rotating freely, when they do that, there's these 3 hydrogens sticking off of the carbons, and if they come too close to each other, they have what's called strain. Now there are different types of strain, but the molecules don't like to be close together like this because they're going to repel each other. So when the single bonds can rotate, they can achieve any arrangement, usually, that allows them to be basically as far apart as possible. And when you did this in Gen Chem, you would have done this with valence shell electron pair repulsion theory. It's building on there, but now we're talking about just carbon-containing compounds, and we're talking about these hydrogens being too close together. So what they do is rotate. So this is actually the least favored because it's going to be the most high energy structure. And what that means is it's going to take the most energy to be able to be in that structure because it's got to hold these 2 hydrogens closer together than they want to be. So the molecule will rotate around like this. It can rotate around, moving this group further away from this group, and it avoids and gets rid of the crowding that we end up having. So this would be the most stable structure or most stable conformation because it's the lowest energy. It means it takes the least amount of energy to keep it. And this one's somewhere in the middle. And we can actually have an energy graph. You may have seen these. I don't know. It depends on where you went, what you did. But you'll have basically something that is really high in energy, which would be this structure. I'm going to just number them 1, 2, 3. And they're going to rotate constantly. So we come up and they're high, and then we have an intermediate, and then we have a low. I didn't mean to draw it like that. I'm sorry. I would erase the whole thing. So we have where we come from our low energy up to our high energy, and there's an intermediate maybe in there. It depends on how many different conformations a molecule can have. I don't want to leave that up there too long. I don't want to worry about. I'll draw another one later, but I don't want you to worry about having to draw those out. But realistically, it's just because in this one, there's so much more space between this methyl group and this methyl group that we're relieving a lot of that strain. So ideally, this rotation is actually limitless. You can have an indefinite number of conformations, and it should be able to, relieve this strain. However, there's going to be something called torsional strain as well, which is when we get into what we're now talking about, which is the restricted rotation, where they can't and they're not free to rotate. So that strain is caused by these repulsive forces that we see that are repelling each other, and they only have certain possibilities once we get into that restricted rotation with the rings. So let's take a look at our first. Well, actually, you know what? I threw this in there. I forgot. This is not in your notes, but this is just basically looking at different types of formulas because I was going to draw out some of these Newman projections for you. So perspective formulas are showing you, and should have had to draw this in lab, but I'm not sure with us being online right now. So when we go the dash and the wedge, now usually one means it's coming into the page and one means it's going out. So it's just showing the 3-dimensional structure on a 2-dimensional piece of paper. So it's showing you perspective on a sheet of paper. This is called a sawhorse projection, where this is a carbon and this is a carbon, and you just draw this going backwards. That's the bond between the carbons, and it's trying to show which direction the hydrogens are in. And then it rotates. This is showing them rotated 60 degrees. Now, these are Newman projections down here on the bottom. In a Newman projection, this is going to show us where it's just a visual representation that shows us a front to back visual. So this dot here, I don't know if you can see that, maybe I'll change colors. So this dot here is a carbon, and this represents the back carbon. So the dot is the front carbon, and the circle is the back carbon. And then the hydrogens are drawn as lines. And it shows us how they line up. So this would be called a staggered conformation, where they're basically as far apart as they can get here. But this is an eclipsed. So I'm going to put the carbons back in red. So here's our first carbon and here's our back carbon. And when they're eclipsed, we're trying to show it on a piece of paper, which we can't really do that well. But these hydrogens are directly behind each other. They actually eclipse each other. So there's 0 degrees difference is the angle between these planes. So there is no space between these hydrogens. So, and this would be the 2 most extreme cases. So these are the most extreme cases, conformations. But the staggered, we see an actual 60-degree angle here between the 2 planes. It's called the dihedral angle. And the staggered would be the most stable. And again, these are the 2 most extreme conformations that we can get. But if you see any of these projections, it's trying to show you this is the front carbon, this is the back carbon, that circle, and it's just trying to help you look at what is happening at that particular carbon and show you how the hydrogens are lining up so you can determine which one is a more high energy or low energy structure. All right, so this is cyclopentane. Cyclopentane is important. I'm not exactly sure what I just did there. I'm hoping you can still see. But anyway, cyclopentane is the most stable conformation of cyclopentane is not flat. So when we draw a ring, a cyclopentane ring, 5-carbon ring, it looks flat. But as you can see here, it actually puckers up, and it's more of a puckered envelope is what we call it, or an envelope shape. So it's more like up, and then we have our other 5. I'm doing my best here, people. I'm not an artist. All right, so coming up and across, something like that, where there's a carbon at each spot here where it comes up, and it does that so it can relieve the strain. So if it was flat, the bond angles would all be about 108 degrees. And if you remember, carbon forms a tetrahedral shape where they want to be 109.5, and we would see an eclipsed structure in some places that would yield much more torsional strain. So by puckering up and folding upward, the molecule is able to relieve a lot of that strain. And so that eclipsing and that torsional strain. So the molecule is actually constantly undulating. So this is moving up or down, and it's changing that position, meaning this one will go down and then this one will come up. So this carbon that's facing up is always moving around the ring. The flap is moving around the ring. And it allows it to relieve a lot of that strain. This is important because we see a lot of these 5-carbon rings that are conformations of important molecules like ribose and, deoxyribose. And there are other, other 5-carbon ring structures in nature, but those are going to be 2 that we talk about in our biochem chapter that are going to be important, that ribose and deoxyribose can form these cyclopentane-like conformations. Now, cyclohexane has 2 possible conformations. Well, it has more than 2 possible conformations, but it has 2 more stable conformations than the others that it could potentially be in. So it's important because it's in all of our carbohydrates and steroids and pesticides and clothing and, structural compounds and many, many, many different compounds produced in nature. If it were planar, all the bond angles would be 120 degrees. Well, if we remember again, carbon wants to have a tetrahedral structure when it's forming 4 bonds with about 109.5 degrees. So carbon is going to relieve that strain by forming what's known as a chair or a boat. So it uses these conformations to allow closer to 109.5, that tetrahedral bond angle, and it can stagger the conformations. When it does that, it's able to relieve some of that strain. So there's technically the boat, the half chair, and the chair that it's going to undulate through. It's going to constantly be moving through these different structures, but the chair is going to be the most stable. So when we do this, okay, this is just 3 different ways to look at it. We have a ball and stick model, and we have a skeletal model. When you go to draw the skeletal model, I don't know if I can do this on the computer very well, drawing these 2 lines that are parallel and then connecting them up and then drawing sort of a triangle down. Basically, you have a person in a chair, like a beach chair, is what this is supposed to represent. They're just hanging out there on the beach chair. So this is pointing down and this is pointing up, is what we see. So looking at this, we have something else that comes into play. We have each carbon has 2 different types of carbon-hydrogen bonds. So these are all carbons. I'm going to write in a different color. These are all carbons, right? Here, 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 and here. We have 6 carbons. But now this gives rise to 2 different types of carbon-hydrogen bonds because we have that restricted rotation. So we have axial, which I will draw in, I don't know, green. So axial that go parallel to the axis. So these are axial. And the axis would be here. So they're parallel to the axis. I don't know if you remember, that means parallel from school. Many, many moons ago, I think I learned that in elementary school, so I hope you guys did too. And then equatorial, we can do in blue. So equatorial kind of points along the equator of the ring. It's pointed out from the ring. So equatorial points, yep, that's a T. I guess it points out to, what do I want to say? Let's say they're, what's an easy word? They're directed. That's probably it. Direction, the direction. They're directed along the equator of the ring. And so here this, oh, of course I did blue. This is showing the equatorial, so that's these hydrogens here, just the equatorial hydrogens. Of course I changed colors on you. I didn't notice. I'm so sorry. And these are the axial hydrogens. Again, along the axis of, wow, okay, I can do this. We're all in this together, right? All right, so these are the axial. When everything in this cyclohexane conformation can be staggered, it's going to give us the lowest energy possible, the lowest energy available. But we don't always have that possibility. And let me just draw out that energy thing for you right now. So if we were to draw an energy graph, I said we have the boat, which I haven't drawn for you yet. I'll show you on the next slide, a half chair and the chair conformations that this is going to go through. So we would see something like Don't judge my drawings again. Hmm. Okay, so these would be the half chair. That's going to be the highest. This would be the boat. I'm gonna tell you what these are in a minute. And these would be the chair. So the chair is, again, these aren't, values. Thank God I didn't write values in there. But in general, they're lower in energy. This is actually something called a twist boat, where the boat slightly twists. It's a little twisted conformation of the boat in order to eliminate what we call the flagpole effect. And I'm going to switch over to the next slide real quick just to show you. Oh, I forgot about that one. We'll come back to that in just a second. The flagpole effect, this is the boat here, and that these hydrogens that are here and here are called flagpole bonds, and they result in what we know as steric strain. So they twist a little bit off to the side so that we don't have that flagpole problem. All right, so during these chair-to-chair conversions that we see it going to this half chair, which is really high in energy. The boat, it does spend a little time in the twist boat, but when it does that, we actually have what's called the go back, okay, called a ring flip, where everything that was axial now becomes equatorial. Isn't that fun? Okay, so that is possible. This is a slide I found. I didn't draw this, but I thought the drawing was really good. And I just really like the handwriting. But basically, this cyclohexane is more flexible. It's not planar, so it adopts these other conformations that we're talking about. So this is the chair, and this is the boat. And the steric hindrance that you can see here between these two flagpole hydrogens, it actually forms this little bit of a twisted boat to relieve that. So the torsional strain and that higher energy can be relieved. And it's showing you where the eye is, which is what I really liked about this. And I felt that I didn't have to redraw it. So whoever made this, I couldn't find your name, but thank you. But it shows you also the Newman projections, which I liked. So this is the Newman projection that shows us that there's a carbon here. I'm going to highlight it instead. So there's a carbon here and here and here and here, and also one here and here. So it shows you how we relate that Newman projection and to this cyclohexane, which is kind of cool. We're not going to go too in depth into this. We're going to kind of stick towards the basic end of determining what is and what isn't really stable. So I don't know if I said this yet. I think it's on the next slide. So after we talk about, okay, we'll look at the boat. We did look at the boat, but this is my original boat picture. This is going to be the one that's in your slides. I'll switch it up, but I hadn't already. So these are the boat structures. We still have the axial and equatorial positions, but the chair conformation is always going to be the most stable. If we have substituents on the ring, this is where it becomes an issue of stability. The more stable conformation is when the substituent is in the equatorial position, because it's going to be pointing out and away from the ring versus up or down where it could get strained by nearby hydrogens or other substituents. So if there's more than one substituent, we always want to put the larger group in the equatorial position if at all possible. If you have two groups that can exist and be both axial or both equatorial, you would want them to be both equatorial because that's going to be more stable. And we're going to talk about what's called geometric isomers or cis-trans isomers that are forming due to, again, restricted rotation. And they're what we call stereoisomers, and I will talk about that in just a minute. But they're going to differ from each other in three-dimensional space. So we're going to see that in 3D space, how they are different. So for one, I want us just to take a look. I want you to pause it, take a look, and tell me which one you think is more stable. So you have to figure out which group is the largest, and is it in the axial position or the equatorial position, and which one is more stable. So pause it, try to figure that out. I'm going to go through the answers. So this one would be more stable because this is tert-butyl, right? T-butyl. And if we were to draw that, it would be C. That's where it's going to the ring. CH3 three times. That's a big, big molecule. This is equatorial. This is axial. So the bigger group is in the equatorial position, and that's where it would be most stable, if at all possible. I didn't mean to do that, but okay. So these are both axial, and these are both equatorial. In that case, we would want them both to be equatorial whenever possible. I'm going to pull something up here real quick. Actually, no, we'll talk about cis-trans first, and then I'll go over that. But I have a couple things I want you to do. First, I want you to try this. I want you to draw the two conformations of T-butyl cyclohexane and tell me in which one is more stable. So I need you to draw them to your best of your ability using this chair, like we said. So draw two parallel lines. That one's too angled, sorry. It doesn't have to be perfect, right? I'm not even going to see it. It's going to be at your house. So draw two parallel lines and then connect them. I don't like drawing it that way. You know what? I say that because people tell me it's easier, but I like to do it this way. So I'm just going to show you how I do it. All right, so I do it like this, and then I try. Mine aren't good though, I guess. When I'm trying to do it on a video, I'm getting nervous, I guess. So I guess it depends if you're pointing up or down, but I would do it like this, and then this, and then I would do this. Nope, that one's got to be lower. See, I'm doing a terrible job. This one comes up here, and that one goes down there. So something along those lines. They don't have to be perfect, and then you have your options. Now, you don't have to draw the hydrogens if they're just hydrogens, you don't have to draw them. And see, mine I drew poorly because now they're going to hit each other, which if you draw it right, it doesn't have to. Anyway, all I'm trying to say is do your best, okay? And I normally don't have that much trouble. I don't know what's going on today. So draw the two conformers of T-butyl cyclohexane and which one is more stable. So you need to pause it and draw them and then determine which one is more stable. I'm going to keep going. So I'm going to do my best here to, oh, I didn't angle that one. I have them in the PowerPoint, but I'm going to draw them like I'm asking you to do. Obviously, we're not going to be able to draw them on Blackboard very easily, so we're going to figure this out. That is the worst chair. I don't know what's going on today. Okay. Close enough. Okay. So we'll draw two of those. Ish. Close enough. All right, so we can have it in the axial position or in the equatorial position. And we need to know which one is more stable. And I'm going to erase my hieroglyphics now and just show you because I put them in here, but I just wanted to show you that it can be difficult, but just do your best. This is going to be the more stable because it's in the equatorial position. So cis, trans, or geometric isomers. When you look up geometric isomers, you're probably going to see something about E and Z. We're not going to go through E and Z nomenclature this semester. If you take a full organic class, it actually might be easier if you've already learned it. I get it. But we're going to stick with cis-trans. And the reason why E and Z might be easier is because you can have more opportunities to use it. Cis and trans are very limited. But cis comes from the Latin, which means on the same side. And trans also comes from Latin, which means across from. So when we look at something that is cis, it's going to be on the same side. So these are actually the same molecules here and here. These are both the same. We just have a ball and stick model and then what's called a edge view model. Here it's tipped on its side. That's why it's darker in the front. And you can see that both of these methyl groups are on the same side. So if we have what's called a disubstituted cycloalkane, so we have disubstitute meaning two substituents, and cis we have two identical, it's doing that to me, okay, two identical groups. We can look and see if they're on the same side of the ring, this would be cis, or on opposite sides of the ring, this would be trans. It's easier when it's on an edge view to see this. But if we're talking about writing this in a chair view, like what we're looking at here and here, it's not always as simple. So I want to go through a very simple little chart I want to give you that will tell you what to do. So the position on the ring, so this would be in carbon number 1 and carbon number 2. That's the position that those ones are in. So if we have them in 1 and 2, you could have them in 1 and 3, or you can have them in 1 and 4. Anything other than that and your position numbers would change. If you want it to be cis or trans, this is what you need to do. So they can be axial and equatorial. So number 1 could be axial, number 2 could be equatorial, or number 1 could be equatorial and number 2 could be axial. If you want it to be in positions 3, in order to be on the same side of the ring, they would both have to be axial or both equatorial. If you want them to be on the same side of the ring in 1 and 4, it's going to be the same as 1 and 2. It would be axial equatorial or equatorial axial. And that is because when we look at, remember our chair view, things are not always pointing the way that they look in this nice side angle view. So for opposite sides of the ring, it could be both axial if they're 1 and 2, or they could be equatorial. For 1 and 3, they could be axial and equatorial, or equatorial and axial. I'm starting to say the words wrong. And then in 1 and 4, they could be axial, axial, or equatorial, equatorial. So that's if you need to draw out what I'm going to ask you to do in just a moment, draw out an isomer using cis-trans. So this is only if we have disubstituted cycloalkanes that we're going to be dealing with this. All right, because they have restricted rotation. The wedge and dash method, remember wedge means they're above, well, in this case, dealing with rings, wedge means it's above the ring and a dash means it's below the ring. Honestly, I'm not that picky. I shouldn't say something. But if you have two wedges, it means they're the same. If you have two dashes, it means they're the same. I don't think we're going to get into the point of this where we're talking about above and below. But if you're going to be going further in organic chemistry, it doesn't matter because some of our chemicals have what we call a front side attack or a back side attack. And it's going to be important which direction this is facing. So that's not always the case with what we're dealing with in this class. So I want you to practice and tell me, are the following cis or trans? These are both the same molecule over here, just a different view, and these are the same. So we have like an A and a B. And I just want to know, are they the same or are they different? Or sorry, are they cis or trans? And you can name them as well. So we have obviously trans. So we start with trans. 1, 2, 3, 4. 1, dimethyl cyclohexane. And here we have cis 1,4 dimethyl cyclohexane. And I think I have them written in there, I was going to say. Pretty sure. So cis below the ring, or sorry, cis on the same side of the ring and trans on opposite sides of the ring. But this isn't in your notes either. I put this slide in here. I want you to draw both conformations of cis 1,3 diethyl cyclohexane. So which one is more stable? Putting all this together. Pause it and try it, and then come back and come through the slides with me. And again, I'm going to do my best to get these horrible things drawn out, right? They're not that bad. I'm just having a hard time today. Why? I think it's because I'm not going low enough there, but whatever. Enough. Why do I keep ending up? I'm not sure why that side came out so big, but we'll do it a little less. Oh, whatever. Here we go. You get it. You get the point. That's all that matters, right? So remembering that we have axial and equatorial. So let's just pick carbon number 1. 1, 2, 3, 4, 5, and 6. And let's just number them both the same so it's easier. We want cis, same side. And if you remember, for 1 and 3, if we want them to be cis, they can either both be axial or they can both be equatorial. So we can look at this and say cis, all right, we're looking at diethyl. So we need to draw 2 ethyl groups, one at number 3, and we can draw them in the equatorial position, or we can draw them in the axial position. So the axial position would look something like this. Why is it doing that? All right, and then here at number 3, if we look here, we would be drawing this in the axial position as well. So we have to get used to where is that located, right? So our axial one goes along the axis, and it's going to be a little harder to see because I'm going to be drawing it here. I keep doing that. So they would both be coming down below the ring at each other, very close to each other. Now, if we draw them both in the equatorial position, this one's coming out and up, and this one is coming out and up. Well, I should say, hold on. Draw it like this, I guess. It's kind of hard for me to illustrate this in this way, but I'm doing my best. So it's going away from the ring. So which of these do you think would be more stable? Go back. Okay. And it would be this one because they're both in the equatorial. So anytime that we can have a group, both groups in the equatorial position, it's going to be much more stable. And the last type of rings we want to talk about are bicyclic. And when I accidentally went forward a second ago, I noticed that there are 2 possibilities. I noticed that my writing was still there, so it didn't do the animation that I wanted. So I'm just going to put it all in there. So if there's 2 or more rings that can be joined, they're called bicyclic or polycyclic. This becomes important. We talk about steroids, things like that. We have a lot of our drugs are fused rings. You are not going to have to worry about naming these for me. I mean it. Do not even consider it for a moment. I put those names in there just so that when you do see these names, you're not like, WTF, what is that? Okay, so this is just on what are we looking at? So these are called fused rings. They're going to be sharing these carbons here. So they're sharing the carbons in between the rings. And then over here on our bridged rings, we have what's called a bridging carbon. So this actually means this carbon is coming up above, I need the laser pointer, up above this ring, and it's bridging it over to this other carbon, forming basically almost looks like that envelope that we saw, right? But it's sharing it between two sides. So this is known as the bridging carbon, and these are known as what's called the bridge head carbons. So if you see any of that in your terminology or any other type of resource, that's what it's referring to. I'm going to stop this one here because then I'm going to go on to properties and reactions.